Okay, now let's do a little bit of, now that we have estimated this data, what do you think of the shape of this curve, now that we have gone through so much trouble estimating it? If you were to describe it?
I mean, bell-shaped, it's fairly symmetrical, close to a normal distribution, but it might be a bit skinny.
Yeah, so it's, well, the normal distribution can be skinny. It's not a standard normal, but so it's a bell shape. It's symmetric. It's unimodal. Looks like you've seen in the first few lectures you've seen a binomial. Could look like the histogram could look almost like a binomial, and then the estimate itself looks like almost like a normal distribution. It has a bit of a bump over here, but it looks almost like a normal distribution. And so the binomial distribution is approximately normal with mean NP and variance n times p minus times 1 minus p for large n, and for p not close to 0 or 1. So the binomial you've seen as you added more and more and more and more and more trials start to become more and more like a histogram of a normal that is not perfectly done. In fact, that's how the normal distribution was invented in the first place, as the limit of the binomial as you increase the number of trials. We'll come back to the normal distribution in great details later, because it turns out that many random variables can be conveniently assumed to be drawn from a normal distribution, to have a normal distribution because of a rather magical theorem that David will cover very soon. So one example of, in fact, the sort of almost a canonical example that you will find of a normal distribution is height, which is sort of one reason why I picked height to play with histogram. But as I did that, I was kind of started to wonder why height should be normally distributed. We don't know yet. You don't know enough statistics to know yet. I just want you to have the question, like, why would height be normally distributed after all? So think about it, and then we'll have the answer after we've seen the central limit theorem. It does look almost normal. Now, we might want to be interested in comparing. We might have two samples, and we might want to start to compare them. So I've shown you some data from Bihar and some data from the US, and I might be interested in looking at the density of these two together. Which one is US and which one is Bihar here? Sorry? Yeah, go ahead.
Oh, no, I think I have a question.
Yes.
But, so is there an advantage to using density over counts, like specifically, or is that just like a choice?
For kernel, you wouldn't count. The kernel is always a density estimation. If you want to look at two things, so in fact, why don't I postpone your question? You'll have a very clear answer to your question for why density is sometimes preferable to counts. It's coming. But for kernel estimates the density. You can go back and multiply to the count. This is because, I mean, the count, you'll have a full answer to your question in a few minutes. So which is Bihar, which is the US?
US is red.
US is red. So there are two ways to know that. The first is that I have not changed the color code. So I had coded Bihar as blue and US as red. So that's one way. And the other way to know is
US peak of the peak of the function, so that we can see that on an average, US female is higher, taller than.
Yes, exactly. So in a red distribution, we see that the mode of the distribution, which corresponds to the peak of this function, seems to be a bit higher, or in fact quite a bit higher. So it looks like the red sample is taller. So it's more likely to be the US sample. That's the first thing that I could learn from this graph.